Hi, this is Derek Mack, and this is the valence bond theory quiz for Chemistry 112. The molecule we are doing is CO32 minus, and we're going to start by drawing the Vesper structure. So the first step in drawing the Vesper structure is to identify how many electrons are in the Lewis structure. We can calculate that by looking at the periodic table and noticing that since carbon is in group 4, there are 4 electrons, and there's only one carbon, so 1 times 4 is 4. There are 3 oxygens, so since oxygen is in group 6, we see that there are 6 electrons, so 3 times 6 right here, and then the extra 2 electrons that come from the 2 minus. That equals to 24 electrons, and we can use that data to draw the Lewis structure. In the Lewis structure, there's 3 bonds, or 3 groups of bonds, and these will be the electron groups we're going to use to find the Vesper structure. So we can write 3 right here, and when you find the Vesper structure, you have to compare the number of bonding pairs to the number of lone pairs to find the molecular geometry. The electron geometry, however, is only dependent on the number of electron groups. So from the 3 electron groups we found, we know that the electron geometry is going to be trigonoplanar. And to find the molecular geometry, we just have to count the number of bonding pairs, which is 3. And since we have 3 bonding pairs, there are 0 lone pairs in the Vesper structure. From here, we just have to find the angle for which the angle between the oxygens around the central atom, which is carbon. So in order to do that, we have to use the hierarchy of pair repulsion. So it goes from lone pair to lone pair repulsion is the strongest, followed by bonding pair. Followed by lone pair to bonding pair, and then bonding pair to bonding pair. In this Vesper structure, however, all of these bonds around the central atom are bonding pairs. So there's going to be equal repulsion between all 3 of the oxygens surrounding the central atom. And that's going to result in a degrees of 120. In this slide, we're going to take a look at the different kinds of ways this molecule can be represented. So in this picture right here, the CO32 minus is represented using the model kit. So each of these gray sticks represent bonds, and as you can see at the top here, there's a double bond, a single bond on the bottom left, and then the single bond on the bottom right. Also, you might want to notice that all 3 of the oxygens, the red circles, or the red spheres, are on the same plane, which is a characteristic of trigonoplanar. Also, another thing to keep in mind is just that there are surrounding electrons around these oxygens. So the bottom 2 both have 6 surrounding electrons, and the top only has 2 because there's a double bond here. In the next picture, it shows the atomic orbitals for carbon, and you can see how it matches the model kit because there are 2 bonds on the top, and then a single bond on the bottom left and a single bond on the bottom right. And you might want to just take note that these angles are all 120 degrees. Okay. And for the next structure, the bottom left one, we're going to notice that the bonds are visualized as either sigma bonds or pi bonds. And finally, in the last structure, we're going to notice that it shares the same characteristics as the other ones, including the angle, which is 120 degrees, the fact that it's trigonoplanar, and the only thing missing is the double bond, which should belong here or on any of the 3 bonds. Now we're going to take a look at the box diagram for CO32 minus. we're going to start by looking at the central atom, which is carbon. So from the periodic table, we know that carbon has 4 electrons, since it's group 4, and so there are 2 in the 2s and also 2 in the 2p. Right now, there are only 2 what we call parking spaces for carbon to bond with oxygen, and we're going to need 4 because there are 3 sigma bonds total and 1 pi bond. So in order to do that, we're going to have to promote this electron to the 2p, and doing so requires an increase in energy. And it can be either one of these 3 electrons that it promotes to. And from this step, we're going to have to hybridize carbon, and you'll know that it's the sp2 layer because shape predicts hybridization, and sp2 is equivalent to the trigonal planar. And so what we're doing here is we're hybridizing these 3 electrons and bringing them to the sp2 layer, and we're leaving 1 electron in the 2p layer to bring over to form the pi bond over here. Also, for CO32-, we're going to have to hybridize the oxygen. So we're going to look at it in its ground state, and we notice that it has 2 parking spaces, and we're going to need 2 parking spaces in order to form 1 sigma bond and 1 pi bond, because this right here represents a double bond between oxygen and carbon. So we're going to hybridize these 3. We're going to hybridize these 3 orbitals and bring it over here. And notice how there are 2 non-bonding orbitals and 2 bonding orbitals. And these 2 bonding orbitals are going to bond with the carbon. So you'll see that this in the sp2 goes along with this right here in the sp2 and forms another electron there. And the one in the 2p right here is going to move over here and form a pi bond with carbon in the 2p. And the remaining 2 oxygens over here are going to, well, it's written as 1, but you can just pretend this is happening twice with 2 different oxygens. So one of them is going to go right here, and then this would be from the second oxygen. It would be placed right there. And that's how the box diagram is for CO32-. One last thing I want to note is that when these electrons come over here, it's not actually giving it the electron, but rather they're sharing it. And it can better be represented if you draw it as an oval around both of them. Lastly, we're going to take a look at the contour diagram for CO32-. So first off the bat, we want to draw the sp2 orbitals surrounding the carbon. And there's going to be 3 of them, 1 for each of the bonds between the oxygens. So we're going to draw 1 here, here, and here. And then we're also going to draw the bonds for the oxygens. So on the bottom 2, since they were single bonds, they're going to be sigma bonds, and it's going to be in the 2p orbital, right here and right here. Then we're going to draw the double bond with the oxygen at the top. The first bond is going to be a sigma bond, which forms when 2 of the sp2 orbitals hybridize, and the other is going to be a pi bond, one pi bond between the oxygen and the carbon, which forms the second bond of the double bond between oxygen and carbon. Also, some key things to note are the sharing of electrons between each bond. You don't want to forget to write those. And that's it.